Another time.
Okay, let's start. Today we are very happy to have our very own PHI PI, Priya Natarajan, also professor and chair of astronomy at Yale. And she's going to tell us about new insights into the formation of the first black holes. Take it
Thank
away.
you. Thanks. I'm really excited to have this opportunity. It's the first time that I'm actually giving the PHI program. So, yeah. But so I want to talk a little bit about what we are really learning about the first black holes. And to just put it into context, I just want to remind you that in 2005, 2006, when I started working on trying to understand how to form the first black holes beyond just the traditional channel of the first stars and stellar remnants, it was extremely unorthodox, to say the least. And this is trying to integrate this picture of how you could form an early black hole and synthesize that into the larger framework of structure formation, because it was becoming very clear that the central supermassive black hole was likely key feature of galaxy formation and structure formation in the lambda CDM paradigm, right? Before that, remember, it was only 1998 when this correlation between the properties of the mass of the black hole and properties of the inner parts of galaxies was actually empirically found. So before I start, I want to give a shout out to several people with whom I have worked over the years who are in the audience: Angelo Riccardi, Fabio Papucci, Nico, who's not here. And so over the years, this is a list of all the people that over the years have been working on various aspects of these first black holes, early black hole seeds, and planting them in the standard sort of structure formation scenario. So this is an outline of my talk. So I'll give you, I think this is a very, very exciting time to be working on supermassive black holes, because there is a really ongoing supermassive black hole revolution from the astrophysical side. And there are great insights from individual sources that I'm going to really focus on the talk today from JWST, but also our understanding of supermassive black hole binaries and therefore populations. So this is the outline, but I want to talk a little bit about our current understanding of multiple seed formation channels and the fact that one can loosely classify seeds into light and heavy seeds. Oh, sorry, I'm really annoying, but I am not able to do that. Okay.
Yeah, I'm not seeing it.
I'm not seeing it anywhere. Yeah, sorry about that. Can you do it?
I think your mouse just has to make it onto that screen. I don't know how to get it there though.
Oh, I don't want to perturb
Oh,
it.
there
It worked.
It did go. It did go.
Oh no.
It's gone again.
There it is. There it is.
Okay, let me
Oh, wait.
Okay. Be close. No, sorry, guys.
No,
I'm
fine.
so sorry. How come this has not been an issue with? Okay. Sorry about that. Okay. So as you all know, there's been sort of an ongoing revolution in stellar mass black holes with LIGO Virgo Cabrera detection. And this is the currently updated version of the chandelier plot. So what I want to the axis got cut off here. Sorry about that. So the most massive thing that you're seeing, that the most massive black hole that they have detected so far is 142 solar masses. Okay. So
What are they?
so this is solar masses. So this is the masses of the black holes. And this is just the masses are here, I think. Yeah, and these are just the events. These are all the LIGO events. So these are the mergers. This is the final mass, the two merging stellar masses and their final masses. Yeah, sorry.
What's the
These are like ranging from 10 solar masses all the way to 100 solar masses are the final masses of these binary stellar black hole mergers. It's just a diagram that is showing you how many you have visually and what the masses are looking like. So these are the electromagnetically detected stellar mass black holes. So this is just to show you that,
What's the peak in the pronounced peak?
the peak.
Yeah.
Yeah, so this is 142 solar masses. So this is a black hole, the most massive black hole that they have detected so far, the merger, the final mass. And these are the two black holes that have merged to give you
And
this.
the
I thought you
arrangement
said
is just
before, no, no, no.
It's
artistic.
just artistic.
It's just
not a-
artistic.
It's not a scientific plot.
Is there symmetry here?
No, somebody wanted to make it look pretty,
That's
so
all.
don't worry, yeah.
Exactly. So
It's just the height.
yeah, it's just the height,
The
the
tallest fellow is the most massive
massive one that.
so far.
Yeah, sorry, it's just, but I just like how it looked.
I don't understand this.
Yeah.
Andy has spent his life looking at symmetries.
Oh, I see. You are
Yeah,
saying-
this looks like some fundamental symmetry, yeah.
As you all have also noted, right, in the last couple of years, last year, NANOGrav and the other international pulsar timing arrays have reported evidence for the stochastic gravitational wave background from a population of merging supermassive black holes over cosmic time. And so the interesting thing is the inferred amplitude that they have for these sources that they've extracted from the data is higher than predicted by supermassive black hole growth and evolution models of quasars. So these models are built assuming that pretty much every quasar that we see is actually a binary, a very close binary. Okay, so that's the basis of that model. And when they, even with that sort of dramatic inference, they find that they are under predicting the observed amplitude. So obviously they're missing, right? Astronomers know there's a large population of obscure quasars that are not optically bright. So if you include that in the census, you can kind of account for these actually. So it's not a crisis as such, except that this is suggesting that essentially the universe is littered with supermassive black holes. So this is where JWST has come in, and I think there's a very amazing revolution that's uncovered. So these axes are real axes. This is a scientific plot. So I have the bolometric luminosity of these accreting black holes as a function of redshift. And so all the points that you are seeing here that are colored with larger diamonds and stars, they are all JWST discoveries. And today I'll be talking mostly about these three sources, which are at redshift above 10, because I'm going to talk about the insights into seeding. And the insights are obviously going to be more salient as we get closer and closer to the seeding epoch, which is at higher and higher redshifts. So to roughly give you an idea, right? So this kind of time scale we're talking about is 400 million to 500 million years after the Big Bang. So really, really early. And sort of this has been really dramatic. And this is filling in very, very rapidly. And I think we're filling in this region. So this gray region is Sloan Digital Sky Survey quasars and some other assorted surveys. And everything that has a solid marking is JWST. So as you can see, it's really quite remarkable. It's starting to fill in. And this was anticipated. We expected this, okay? So none of this, you might read this in the press, oh, Anna, we did, and that's why JWST, right, was actually built.
Even the high Z.
The IZ too. I mean, we weren't sure how many we would find there. So, I mean, the fact that we found these three is quite remarkable. And so there are many surveys, and all of them have various acronyms, and you can look them up. So this is a compilation. So the other exciting thing that's happened is that we've also started, and I think that we heard Zhao Fen talk about this in a previous colloquium, where we are starting to actually look and find with JWST the host galaxies of these quasars out to 7, direct imaging of the host out to 7. That is remarkable as well. So we can actually study more detailed properties like the morphology of the host beyond just collecting the photons, converting it into a stellar mass, right? Which is sort of what has been done till now. So this is like another really new window. And one other reason I think we have a revolution going on is also some work that's being done here that I want to highlight, right? So the other revolution, other than the observational revolution, is really trying to understand how these black holes are fed. So how gas from very large scales actually makes it all the way to very small scales. Because fundamental to understanding our growth of black holes is the accretion rate onto black holes. Because it's become very, very clear that accretion is the primary mode for, by and large, the entire black hole population to grow over cosmic time. There are specific cases, specific times and environments in the universe. Early universe, you have a lot more mergers, and the late universe, the most massive black holes still have mergers and are growing via mergers. But by and large, accretion is really how the bulk of the mass of black holes is assembled. So this is a very fundamental problem. And here,
Massive black holes, but
by
They
massive,
don't-
I mean anything above 10 to the 8 or so, supermassive, sort of the higher end of
The
the
higher-
super-
the
higher mass end.
and it's still kind of a mystery, the less massive ones.
Not really, not really. I think are you referring to the intermediate mass black
Yeah,
holes?
yeah.
I mean, it's not a mystery. They're a mystery in the sense that we've not detected them in the proportions that we expected, or we expect to find them. But we are starting to uncover that population in the centers of dwarf galaxies, especially nearby dwarf galaxies. They're going to be faint when they'll be the faintest accretors, so they're more challenging to find. So this is to give a shout out to Heron Cho's work here with Ben Prather, Kungi Su, and of course Ramesh Narayan. So what's interesting here in these simulations, we are finding that the assumptions that people have made in building theoretical models of black hole growth or simulations of how much gas actually makes it to the horizon are really overestimated. Partly because, as you know, cosmological simulations do not have the resolution to go down to the horizon. So they model the flow at the Bondi radius, which is way outside, 10 to the 5 gravitational radii or so. And they just assume any gas particle that crosses the Bondi radius eventually gets accreted. It turns out that it doesn't. Actually, 1% of the stuff that crosses the Bondi radius actually makes it in. So
What's
there's
the boundary?
the Bondi radius is the sort of how do I explain the Bondi radius? It's the radius at which the accretion flow, it's an exact solution where gas from infinity is ideally, when it crosses the Bondi radius, is going to make it to the black hole. It's where the gas flow from, wouldn't you say that, Ramesh? Would you-
It's the gravitational sphere of influence
Influence.
of the black hole.
But it goes to infinity.
No,
Yeah.
but the gas from
No.
infinity, therefore, when it reaches there, will ultimately make it in.
The black hole is sitting in a galaxy. Inside the Bondi radius, the black hole is the boss.
Boss.
Outside
So
the
it's the
Bondi
galaxy.
radius, the black hole is a perturbation on the galaxy. The galaxy is the boss.
And that takes
potential
into
web.
account the thermal energy.
Everything, yeah, it's,
Yeah.
they're all of the same order, yeah, so. We can talk in more detail, but yeah, it's a very characteristic radius that,
And it's a radius that can be modeled. It's a scale that can be modeled in a simulation as well. So it has physical meaning and it can be modeled. We can't go, people are not able to go much further in and accurately model the flows unless you do a simulation that is a GRMHD simulation, which is a very small scale simulation.
10 to the 5, what is the
Gravitational
small
rate.
number 10 to the 5?
it's just the velocity of things in the galaxy. Yeah, so the typical
yeah.
V squared,
Yeah,
V
yeah.
squared in the galaxy is 10 to
Yeah.
the minus 5 C squared.
So anyway, here, so what we find is there's a real suppression of the amount of gas that flows in. Okay. So here's our current understanding of the seeding situation. So we believe that there's a class of light seeds, which are seeds that you get from the remnants of the first stars that form in the universe that are referred to as POP3 stars. So the initial mass function of these population 3 stars is very poorly understood. we have not yet detected a single POP3 star or a cluster of POP3 stars, even with JWST. We have not yet. So that's uncertain, very highly uncertain. But we believe that the mass function was tilted high. So the first stars were actually more massive than the stars that we see forming in our vicinity. And therefore, the remnants are going to be, the remnant black holes are expected to be between 10 to 100 solar masses, the initial seeds from those stars. And, but that is insufficient. That mass is insufficient without a lot of fine tuning to start explaining supermassive black holes that are in place so early in the universe. In fact, these seeds posed a problem to explain a billion solar mass quasar powered by a billion solar mass black hole at redshift 7, which was already detected about 10 years ago. So there was a lot of fine tuning. You could do it, but you would have to fine tune the formation. There wasn't a sort of a natural way to explain it. So that motivated people to start thinking about other ways to make black holes, the first black hole seeds, that would be more massive than the remnants of the POP3 stars from the get-go. So there were a couple of settings that were available cosmically. So first, we know that you don't form a single star, you actually form a star cluster of population 3 stars. So most likely you form a dense nuclear star cluster, and one can imagine dynamical ways in which, they could all give you little black holes that could then merge. And so if you kind of do the inventory, you could build up a seed of about 10 to the 3, 10 to the 4 solar masses. Yeah.
You mentioned fine tuning earlier. What kind of parameter space are you fine tuning?
We're talking about accretion rates, and therefore the environments of the things that they're sitting in, the halos and the galaxies that are. So I'll come to that in a little bit when I talk a little bit more about this model that works, right?
Thank you.
So these are nuclear star clusters are a cosmic setting from which you are likely to be able to assemble a seed black hole at pretty high redshift, maybe between 10 to the 3, 10 to the 4 solar masses. So this is, so from the get-go, you could have something that's, with a little bit of a delay that takes into account the formation of the nuclear star cluster, the remnants dying out, and then merging. So this, again, timing-wise was a resolution, but we were not satisfied with that, and we started looking more in more detail to see if there are other kinds of astrophysical processes that would allow you to assemble from the get-go right away 10 to the 4 to 10 to the 6, even up to 10 to the 6 solar masses right away. And so we found such a setting. And that's that sort of setting, which is what we referred to as heavy seeds. So there are many avatars of those heavy seeds that you could potentially form. There are many models, as I'll show you. And the model that I originally started working with my postdoc, Giuseppe Lodato, 2005, 2006, was a very simple model of direct collapse of gas. And I'll elaborate on that setting a little bit further on. But what was interesting about this particular astrophysical setting was that there are places in the cosmos. So if you go into cosmological simulation and look at the conditions that you need for this process, they exist. And they are not as abundant but as sites where you would probably form the light seeds. But we were very, very intrigued that you are able to produce a seed that is quite massive from the get-go at redshifts of about 15 to 20. So very, very early on. So if JWST was going to find black holes, a supermassive black hole, say at redshift 16, redshift 17, 10 to the 6 solar mass black hole actively growing, not a problem, according to our scenario of direct collapse, right? So, so I'm going to be elaborating on this particular channel for forming black hole seeds later on. And I want to motivate a little bit. People often ask, well, why look for another channel? Well, there was the problem with the timing crunch, right? So there's another issue, as I mentioned. So these are simulations of the formation of the first stars. And these are actually the masses of the first stars, not the masses of the black holes that will result from them, but the masses of the first stars. This considerable uncertainty But, you can maybe form these massive stars that are a few hundred solar masses to start with. So note that their remnants are going to be less massive, okay? So the timing problem, coming back to the timing problem, these seeds are going to be too light. Furthermore, in these very simulations where people form these first stars, and then they model them as their remnants as sink particles. So this is a slice from one of those simulations. What they actually find is because they form in clusters, they kick each other around, and they actually are mostly never sitting in gas-rich regions of these early proto-galaxies. So they don't grow that dramatically. At least this is what they claimed. Abel, Weiss, Turk, and Alvarez in their simulations using ENSO, which is this code that can actually resolve these scales. I mean, the details are irrelevant. The thing is, these are simulations where they are able to resolve the scales that they claim that they are, okay? And what they find is that there's really not very much growth from when the seeds form and they are inserted as sinks into these cosmological simulations. And by redshift 8, they don't grow that much. So they can't really easily give you, of course, these are small boxes, they may not be representative. There are caveats. But the interesting thing is that if you form them in a cluster, the dynamics of the cluster does not ensure that they end up in regions where they can grow dramatically. So, I mean, what is the evidence for light seeds, right? So, as I mentioned, well, LIGO is finding stellar mass black holes. So we know that stellar mass black holes form, but we know that many of the most massive ones in that chandelier diagram that I showed you actually form from multiple dynamical steps, right? We're not seeing them, they're not forming at that birth mass. They are merging, many of them are a product of multiple mergers and so on.
Yeah, that's a statement from the demographical distribution.
Absolutely, yeah. And the number of channels that you have for stellar mass and their settings, the environments in which they form, the binaries from which they form. And so as I
Is there
mentioned,
some kind of statistical analysis of the
There
number of
is.
these ones that related to the density of number of ones that are, in the
yes,
hundreds
there are a
of-
lot of analyses that Fleur, Brook-Garden, and Selma, Demink, and others have done on what fraction. So at the moment, at least 60 to 70% of the black holes that are detected by LIGO have gone through multiple steps and processing before we actually detect them. We are not seeing them at their birth mass.
Yeah.
So, and so as I said, right, earlier, 142 solar masses is the most massive one, and that formed from the collision of 85 solar masses and the 66 solar mass black hole. So these have formed via multiple dynamical processes. And then interestingly, we find that there's some seeding signatures that might survive to late times in very specific environments. I'll come to that later. So one such thing is the black hole occupation fraction in dwarf galaxies. Most of the seeding signatures are unfortunately erased as we go to late cosmic times because of the complexity by which black holes grow, the complex set of processes by which galaxy mergers as well as accretion. And so obviously we needed an instrument like JWST to go as close to the seeding epoch as possible. So then, there have been claims that, well, you can all see where this is going, right? What is the real issue with light and heavy seeds? With light seeds, you need a lot more time, or you need super Eddington accretion to grow very rapidly to give you the very, very massive black holes earlier and earlier back in time, right? So you need to have super Eddington accretion, right, in order to do that if you start from light seeds.
What's super?
Super Eddington accretion. So the Eddington rate is the sweet spot when the radiation pressure sort of balances the gravity of the black hole, right? So you get a sweet spot accretion rate for a black hole. That's the Eddington rate. So super Eddington accretion is circumventing that rate, which means you need a very specific geometry, a change in geometry. You need something like a puffed up disk or the tori, the kind of stuff that Ramesh is an expert on, So you need another kind of geometrical feeding setting to circumvent that sort of sweet spot. It can happen, and there are a couple of cases of supermassive black holes where we think super Eddington accretion is happening. But what we don't actually know is the energy output that comes out, the spectral energy distribution of a super Eddington accreting black hole sitting in a galaxy. We don't know whether it's going to be X-ray bright. There's no consensus at the moment. Whether it'll be optically obscured, will it be optically bright? Will a lot of the radiation come out in the X-rays, or will it be X-ray weak? These are completely unsettled questions. So, and
the radiation pressure depends on something about the plasma around.
yeah,
the black hole,
yes,
and
absolutely.
we
The
know-
Thomson
we-
cross section.
We know enough about that it's kind of a robust.
We do. It's fairly robust.
Yeah.
So, there's really not enough consensus. I'll come back to this yet about super Eddington rates. And essentially, the physics allows you to have multiple channels to make the first black hole seed. And so I just want to point out, and the key, as you can all imagine, right, the key clue to the nature of seeds really lies in the relationship of the accreting black hole to its environment. So different seeding channels, the way you may be able to discriminate them, if you can actually access the sources themselves and their hosts and the host properties, that's really the key clue. And there are other multi-messenger clues that we'll talk about later as well. Okay, so this direct collapse of gas. So it turns out that there have been many settings in cosmological simulations and kind of semi-analytic models where people are able to see the progression of collapse of gas to very, very dense, compact regions that will inevitably form a black hole. So one example, so there have been many ideas that have been proposed, and I will be sort of highlighting 3 that are extremely well developed and look very convincing. So this is a formation scenario for the first black holes that could start operating even at redshifts beyond 20 or so. And so this is work that's led by Latif, Weiss, Reagan, and Whalen. And this is a simulation. It's a small zoom-in simulation of a small portion of the early universe where you have a collapsing halo and you have gas that is rapidly collapsing. And so these are adaptive mesh refinement simulations where you can start refining a region starting out from 100 parsecs all the way down to about 0.02 parsecs, right? So these are sort of state-of-the-art simulations. And what they are able to not only focus down in space, but they're also able to follow. It's getting denser and denser beyond a point they will not be able to follow the fate. So as you all know, no one has actually formed a black hole in any simulation yet. So the gas gets dense enough that it is going to inevitably collapse and give you a black hole. So what they find these little turbulent pores that form, and these turbulent pores start to get more and more compact and denser and denser. And so this is a setting where they find that from very turbulent cold flows that we know exist in the very early universe, this is within all the standard paradigm, and they start seeing collapse at about redshift of 25, okay? And inevitably, these regions are going to give you some kind of seed black holes, and these seed black holes is direct collapse of gas. And the masses, the estimated masses in these white circles, though that's what is expected to collapse in, is of the range of 10 to the 4, 10 to the 5, and even 10 to the 6 solar masses from the get-go. So we are looking at a supermassive black hole that could form already at redshift 20 if this kind of mechanism actually works, right? And so this looks feasible. So it's quite possible that you can make, of course, the question finally is, how many regions of the universe permit this kind of collapse, right? So it turns out these regions are rare, but they do exist, right? And so this is sort of a bona fide way of making the first black holes. So this is the model that I worked on earlier that I mentioned, starting in 2005, 2006, and then over the years, refining this model. we started out as an analytic model because there were no simulations that could actually track this particular channel. So this is also a very specific setting where you have a dark matter halo that has collapsed and has virialized. You have the gas that has fallen in, and this gas settles down into a disk because there's non-zero angular momentum. And then this disk actually has a global instability. It forms a bar and a bar within a bar, and then it collapses directly without cooling or fragmenting. So the idea was that you have to circumvent cooling and fragmenting, i.e. suppress the formation of stars and directly collapse the gas to the center of the halo. So we were able to show that this is a mechanism that can work, and once again, can give you seeds ranging from 10 to the 3 to 10 to the 5 solar masses very, very early on in the universe. So one of the nice, cute things about this model, which is sort of was our motivation as well, because we are starting out from the setting of a dark matter halo and a galaxy, a very specific cosmic setting, we can actually pin down and predict the properties of where such seeds would form. What would be the property of the host that such a seed would form in? And so that was the power of this model. And so this is the cosmic setting in which you would form that kind of direct collapse black hole. And so here is the setting. So the setting is you have a galaxy that has formed its first generation of stars, those POP3 stars we talked about, they have formed. And then because it's cold dark matter and it's hierarchical, you have satellites. It will have, this a parent galaxy will have a lot of satellites. So imagine you have a satellite that also has collapsed, is an atomic cooling halo, 10 to the 4 Kelvin. And now it's irradiated by the Lyman-Werner photons from this stellar population. Why do we want this irradiation? Why is that critical? To prevent further cooling, fragmentation, and star formation in this little satellite halo. So we do not want star formation, right? We want to suppress star formation. We instead want to form that pre-galactic disk, and then we want that disk to go unstable and give you a direct collapse black hole. But then, given that this is a satellite of this parent, as you know, in cold dark matter, this satellite is going to merge with the parent. So this direct collapse black hole that formed in this halo would merge with this galaxy. And what is intriguing when you actually do the computation of the masses, the halo masses, and the setting in CDM, you find that this resultant object will have very peculiar properties in the sense that the mass of the black hole will exceed or be a very high proportion of the mass of the stars. The stars will be subdominant in terms, not just in mass. Therefore, once this starts growing, for a period of time, the spectrum will be dominated by the accreting black hole and not by the stellar component. And so we dubbed this sort of overmassive black hole galaxies, and we realized that this is a transient population. The reason this is a transient population, as you all know, by the time you get to redshift 0, there's a correlation between the mass of the black hole and mass of the stars in the bulge. And remember, that's the mass of the black hole is 0.01%, right? So it's a really tiny fraction, 10 to the minus 3, 10 to the minus 4 of that of the stars. So the stars start to dominate. So at some point, you're going to flip. So you're starting on this correlation for these sources. The black hole dominates, the mass of the black hole is comparable to or is even 10% or something like that, quite large compared to what we see in local galaxies. And so this is a very clear-cut signature that we realized, and therefore we sort of calculated what are all the properties, what are all the observable properties of galaxies that would be going through this stage that would have been seeded by a massive, like a heavy seed at high redshift. In contrast, obviously you want to understand, right, in terms of discrimination, that if you had a galaxy and you had a light seed that forms, so this is the first generation of stars, of 3 stars, let's say the most massive of them lives its life out and leaves behind a remnant black hole, then at the same epoch, a galaxy that was seeded by a light seed versus a heavy seed would look very different spectrally. So this would be, a black hole that whose mass is likely maybe like the local relation or something like that. It's not going to be much more massive than the stars or even comparable. And the spectrum, therefore, will be dominated by the stars. Okay, so we realize that, and I'll show you those very specific predictions later. So I just want you to ponder a little bit, right? So I think the reason, at least I have been sort of fixated on this particular model, is the fact that it has a very clear-cut observational signature. And so you can discriminate. And as I showed you all those other sort of the other channel that I showed you with simulations, people are they haven't reached the point in simulations where they can even talk about the host galaxy. I just showed you, just see turbulent cores. So we are at a stage there, computationally, we are at a stage where we can only say that you can form some very heavy seeds.
I have a question. Is there a difference between like the dark matter halo in this scenario and this scenario?
Well, obviously, there's really no difference other than the fact that this process is likely to happen in lower spin dark matter halos.
Mhm.
So we draw them to be preferentially the formation of that disk, that pre-galactic disk, and its collapse will be facilitated, will be faster in a low spin halo. So, dark matter halos are born with a range of spins, right? So it's a log normal distribution. So it looks like this. So this is P of lambda, that's the spin versus lambda. So our argument is that, preferentially low spin halos. So that's all we want in terms of conditions. Yeah.
Just making sure, your direct collapse black holes come from collapse of halo.
No, of the gas, of the gas. It's the gas. It's the pre-galactic disk that directly, it's baryons. Yeah, all baryons.
Okay.
It's the usual, nothing unusual there.
How massive the galaxy?
It's a higher proportion of the mass compared to the mass of the stars. So, the M sigma relation, right? At redshift 0, the mass of the black hole, sorry, not everyone can see this, is 10 to the minus 3, 10 to the minus, or 10 to the minus 4 of the mass in stars, roughly speaking. So it's this ratio that I'm talking about. So for a direct collapse black hole, this could even be MBH comparable to M star, or MBH roughly, just 10%. Right, so much more massive than what we see in the nearby universe. And so the interesting thing is, right, if these objects exist, and I'm going to argue that we have found one, and maybe two, that this relationship is going to flip. So the stellar assembly, so there's a growth history that this implies as well, right, of how it changes and how you arrive at redshift 0. Okay. So so people have riffed on our model, and there's another model that was proposed by Barrow and Wise. And here is the same setting. You have an early starburst galaxy, that population 3 stars, you have an atomic cooling halo, except this guy's not a satellite necessarily. Okay, it's just a nearby halo, right? So this is a different setting. Once again, you do form a direct collapse black hole. And then accretion onto this black hole will produce, a lot of radiation. You have ionizing radiation, but then you could also form stars, and you could have an H2 region, and this whole thing could be sitting inside an ionized bubble. Slightly different setting, but and they say this, so the direct collapse black hole now, instead of being associated with a subdominant stellar population, will be embedded in a bright H2 region. So just ionized gas would be just sitting in the center of ionized gas. And so they then predicted what the colors of such objects would be for the purposes of detection by JWST. So these are different bands in the JWST wavelength windows that JWST is sensitive to. And they showed that through these various phases, it would fluctuate. And there are periods of time where it would be bright enough to be detected by JWST. So it would transit through these changes of these phases. And there'll be a period of time where it could be bright enough. We have not yet detected anything like this. It needs to have a path. They chart a path in this color space, and we have not yet detected anything quite like this. But this is, another scenario where you could, cosmically valid scenario. Then another way to do direct collapse that people have investigated and now find in simulations is at later times, not at redshift 20 and so on, but at redshift 8. This is one in which this is standard cosmological simulations where you have mergers of two galaxies that are extremely gas rich happening at around redshift of 8, so much later in the universe. And what they find is that you form, when you have two gas-rich galaxies and even independent of whether they both have central black holes already or not, when they merge, they actually produce a nuclear supermassive disk once again. So it all comes down to little disks that will go unstable and that will give you direct collapse, okay? So this is another setting in which you can form this nuclear supermassive disk, and then you can actually form a seed. In fact, so this is work done by Lucio Meyer and my former graduate student, Pedro Capello, now at Zurich. And so what they found is here, again, you could end up with a black hole seed that is even 10 to the 6 solar masses to start with, okay? But this happens at redshift 8, this kind of thing, because you need to build up a gas-rich galaxy first before you actually crash them to get the right setting for this, right? And so what's interesting about this is that this kind of mechanism can actually account for the bright quasars. So the bright quasars at redshift 6 were found to be powered by accretion onto 1 billion solar mass black holes, right? So if you form something at redshift 8 with about 10 to the 6, 10 to the 7 solar masses, they don't have to grow very much. And there's no timing problem. And you can grow by even piddly accretion. You don't need super Eddington accretion. You don't need any special conditions. You can just grow and you can account for that. So that's kind of attractive thing about this model, except that, it's a good explanation for slightly later redshift phenomena. So, so I should just point out here that the way seeding is implemented in cosmological simulations is ad hoc. Okay, so they cannot actually form a black hole. So most of the simulations have formed black holes. They insert a sync particle that's 10 to the 6 solar masses at some redshift, with some conditions on, the halo gas density has to be above a certain threshold, and then they will plonk a black hole into that halo and let it evolve. So Astrid is a new simulation that I've been very excited about because they have experimented with a different seeding paradigm. So they've implemented our initial mass function for direct collapse black hole seeds in the very early universe. And the conditions that we required for that seeding mechanism to work. And so they've implemented that. And what they found is that there are actually pockets and halos at later times as well that satisfy those conditions. So you can actually form the direct collapse channel that I first discussed in our work. You can form that even at later times. Lower masses, but even out to later times. And Astrid actually implements that. So we've been working with Astrid to try and see whether we can go back, because what we can do, as I said, the relationship between the host galaxy and the growing black hole is the key to discriminating multiple seeding scenarios. So in a simulation, you can obviously go back and see what those relationships look like. So there was another model that, for continual seed formation. So we proposed this idea in 2014 that in fact, some of these conditions to form early seeds, maybe you form them light and then you amplify them very rapidly into a heavy seed, that can happen in some other cosmic settings. And this is a favorite setting of mine. And this is now finally sort of catching heat with the community. And that is, you have, again, a very early galaxy where you have formed the first stars. Those are the yellow dots. And you have the first one that has collapsed and given you a little black hole. this black hole is actually like a test particle. It's going to scatter off the stars. It's not necessarily going to be at the center because it's not that massive, but it's going to be feeding gas. It's going to be wind-fed accretion. It will keep gaining mass and then eventually become massive enough and settle into the center. And this can happen in a gas-rich nuclear star cluster. These exist in the very early universe. And so you can start from something that is maybe 10 times the mass of the sun, like a light seed. And within 1 million years, you can grow it to, again, 10 to the 6 solar masses in this setting for a certain zone. And so this, it starts out as a wanderer, then it ends up as a center.
And it's
So-
accreting with
Yes,
eating stars? Or
yes,
just
yes. Yeah.
Eating stars.
No, gas.
Yeah.
Yes. It's scattering off the stars and moving around, but it's eating gas.
Said it exists, do you mean that we have observed it using
JWST starting has found some objects that are looking like nuclear star clusters. Okay, so and then this picture, as you can see, it's very interesting dynamics. It was a cute dynamical problem, but was able to show that this process, this dynamical process, may not go to completion. Like you may not end up with all the gas that's in here. Potentially, all the gas that's in the nuclear star cluster can be accreted in principle by this black hole. With super Eddington rates or whatever, that is going to be really gas supply limited. If you have the gas, that can be accreted, right? And so was able to show that this end point of what the final mass that you end up with for a seed can actually range for this wandering setting. You could get something that stops at 5 to 10 solar masses, few hundred, and go up to 1,000. So this is an amplifier where you can make a seed very rapidly of say 1,000 solar masses. Okay, so here I'm just showing you that there are many, many ways to go beyond. And so I should point out that these ideas of dynamical mergers in slightly different contexts have been pursued by many other groups. And the bottom line is roughly the same, that you can easily get 10 to the 3, 10 to the 4 solar masses in the center of a nuclear star cluster. Okay, so how are we going to discriminate? So let's come to the idea. Okay, I've shown you all these different ways to make heavy seeds. How do we actually discriminate between seeding prescriptions? As I said, mostly a lot of the signals, the primary signals, are at very high redshift. So this is actually work that Angelo did for his thesis, and this is showing the luminosity function of quasars. So it's the abundance of quasars, the number per cubic megaparsec as a function of their bolometric luminosity written in solar luminosity units. Right? And what you find, for the purposes, the details are not that relevant. The cool colors that you see are the propagation of quasar growth and black hole mass assembly from heavy seeds initially from the direct collapse model that I discussed. And the yellow and the warmer colors are light seeds. So we are starting with 2 different buckets of seeds in the very early universe. I think it's what, redshift 25, Angelo, or 30? When did you start?
20.
20, okay.
Yeah.
So you start at 20, and then you grow them via different accretion prescriptions. And these are, the MSPL, et cetera, different, accretion growth prescriptions. So the black holes are growing here by mergers and by accretion of gas. And this is the prediction for the number that you should see, number of accreting black holes that you should see. And notice that the discrimination between the two starts to grow at higher and higher redshift. Of course, it's going to be very, very challenging to find these quasars at these redshifts, at redshifts of 12. Hey, but JWST is inching us there, right? It's getting us there. But remember that we really need to see enough to be able to discriminate. And the discrimination is in the bright end, right? So this is the brightest ones. And thankfully, those are the ones. But it turns out that there is another more clear-cut signature of seeding, and that has to do with the events that LISA will likely detect, the merger events. Because remember, these black holes are growing via mergers and accretion. So these are the predictions for events. So there are many uncertainties in this, right? So the key uncertainty in terms of LISA predictions, the entire community is facing this big challenge, which is we don't know the merger rates, right? The merger rates are uncertain because we don't know about all the physical processes in detail that can actually affect the merger in the centers of galaxies. So it appears that once you scatter off all the stars, then it looks like you definitely need gas or something else to lose angular momentum in the binary orbit of the supermassive black hole binary and start shrinking. Of course, once you shrink close enough, there's a critical separation after which the angular momentum loss is via gravitational waves. And then you very, very rapidly shrink and merge. There are many uncertainties. Biggest uncertainties are the dynamics, okay? And so here, broad-based, we decided, okay, optimistic case, let's say that, every galaxy merger is going to have the black holes merge also. That's P merge 1. And P merge is 10% is a pessimistic case. Only 10% of the time, your black holes will actually merge. And once again, you find, so this is again, the light seeds are in warmer colors and the heavy seeds are in the cooler colors. And so what you really find is that the number of events, this is the number of events for 4 years as a function of redshift. And LISA is agnostic to redshift. It should be able to detect all these events across redshift, right? And so you'll see a real difference in the number of events that are predicted if you have heavy seeds versus light seeds. So there's very clear discrimination here with gravitational wave coalescence and mergers, okay? So I think this is an update. So I want to plug this work. This is new work that Angelo has done. In the work that I showed you earlier, the spin of the black hole was not taken into account. We didn't worry about the spin. We were just growing the black holes. So here, guided by work on the EHT data sets and Ramesh's work on trying to understand different accretion modes, Angelo has implemented spin evolution. So with some basic assumptions about what happens when you accrete. Do you spin up? Do you spin down? What happens when you merge? You have a prograde merger, a retrograde merger. So it's a semi-analytic model, but it's propagated over cosmic time. And so once again, you can see that there are differences. Spin might be an interesting discriminant. There are clear differences in the predicted number of events that you would observe, okay, as a function of spin. And so these are for the light seeds and these are for the heavy seeds. And of course, there are assumptions obviously made here about MAD and SANE. So the accretion model, the different accretion models are adopted here compared to the previous plot that I showed you. Okay, so I mentioned earlier that there's actually one potential seeding signature that might survive to late time. And it turns out that that is the black hole occupation fraction. So it's the fraction of galaxies of a given mass in stars, their probability to host a black hole. So you can go out and measure as a function of stellar mass. And so now we are able to push down to dwarf galaxy scales. And what we find is that, so the dots that you see are the data from Jenny Green's survey, and the boxes are our semi-analytic model predictions. And so what you see here, the data, the square data is from X-ray data for occupation fraction, from Elena Gallo and others. And so what you see there is, the heavy seeds with a particular accretion model. The data is kind of looking interestingly aligned with it. So I wouldn't push it too far, but I'd say that there's some sort of evidence in support of heavy seeds. Okay, let's now go back to the direct collapse, the signature that I've been going on and on about, which is the relationship between the stars, the mass of the stars in the host galaxy and the black hole that it hosts at very high redshift in these OBGs. So I just want any excuse to show this graphic. I just love it. It's starting from heavy seeds. Angelo made it. So starting from heavy seeds, This is the progress by accretion and mergers of that population. And remember, this is the plot we have at redshift 0. This is that correlation that I mentioned where the mass of the black hole is about 10 to the minus 3 or so, except this is now in units of the velocity dispersion of the stars in the host galaxy. So you can see that, what you saw with the clock is that if you start out with heavy seeds, you can nicely reproduce the observed relation at redshift 0, which means that you start out with a relationship where the black hole is overmassive, but then by the time you get to today, it gets to be about 10 to the minus 3. It falls on this relation. So these are data, the points that you see there. Okay. So what are the spectral predictions that we made for those two different scenarios? So once again, this is the energy output in the JWST waveband. So this is about 1 to 20 microns. And these are the spectra that, once again, the cool colors, the warm colors, remember, for the heavy seeds and the light seeds. And what you see here in black are the sensitivity limits for JWST in these particular wavelength ranges. And so anything above that would be a booming signal. Anything below that, you're not going to be able to detect. Okay, so that's the sensitivity. So what you see here very clearly, so this is not redshift, this is the metallicity of the stars. Remember, we had this accreting black hole that formed in the satellite. It merged with the parent that had stars in it. So this is the metallicity of those stars. That's a key parameter. And what we find is that these two curves are the metallicities of the stars, if it is low metallicity versus zero metallicity. And what the thing to note is that there's a window here where there's a very clear feature in the spectrum. There's a sharp upturn and then it is flat. Okay, so this is the feature that we predict, right, for this particular class of objects. And this we predicted at redshift 9. So this is, assuming that the system has formed and it's now at redshift 9. So I should point out that it was Fabio's work with his GEMS code that really helped us come up and make these spectral predictions. So this is for the other setting where you have the light seed. And notice that you are below the sensitivity limits by and large. Occasionally, you may skirt a little bit above, but you're really not going to be detectable. So in 2017, we published the paper with Fabio, Angelo, and other research members of my group, arguing that if this mechanism operates in the early universe, then we should see these objects at redshift 9 or 10 that have this key property that the mass of the black hole is not small compared to the mass of the stars. It's actually overmassive compared to the local relation. Yeah.
What about X-ray binaries? Like there could be many X-ray binaries from two stars or early two stars, and they will be very bright.
Yeah.
In the X-ray bands, similar to your and so I was wondering how this scales with the models.
Yeah, so we have not looked at this contribution of massive X-ray binaries. We really looked at the stellar population, just the full stellar population, and evolved that. We did not look at the contribution. Or you're saying that you don't even have an accreting black hole and you just have X-ray binaries?
You don't have the big HEN, you only have the X-ray binaries.
Right. So then the question is the fine tuning of how many of them would you need and how bright would they have to be, right? So that I don't know. I don't know the answer to that. Okay.
Came out earlier this year, it looks at the X-ray flux from top 3 X-ray binaries, and you can just essentially, this takes our top 3 unleashed model, and so we can predict fluxes.
Okay, great. No, thanks. I'll take a look at that. Thank you so much, Ralph. By the way, that's Ralph Klesson. He's a Radcliffe Fellow this year, and he's worked on the first stars. Yeah, no worries. Okay. Okay, so what am I doing? Oh my God. Okay. Can I just go over time a little bit, please? Okay, I'm just gonna do it. I'm not gonna ask permission to do it. Okay, so, many of you know, I also work on gravitational lensing by clusters. These are clusters that act as dark matter telescopes. And I never thought that my two interests would collide so beautifully. So it turns out that some of the best ways to look at the very early universe is through these gravitational lenses, these cluster lenses. And oh, that's right, Ramesh, you wrote the review on this, right? Gravitational lensing. Yeah, I mean, I think I've mentioned this a few times. A lot of times I used to be confused with Ramesh Narayan. And they would say, oh, wow, you look really young to have written that 1972 paper. I would, early on, I would say, well, I wasn't even born then, whatever. And then I said, what the heck, I'm just going to say yes. Yes, thank you. Yes, that review paper is fantastic. Non-committally didn't say that I did it, but yes, thank you.
So
But
is
anyway,
that because of your surname?
pardon?
Is that because of your last?
Yes, Narayan Natarajan. Yeah, that's the only reason.
Nobody in India would be confused.
Exactly.
But everywhere else, people think it's the same name.
These are regions.
Yeah,
Right.
it was another Narayan. It was a Narayan Murthy.
So anyway, these are regions. These are all various mass models for a cluster. So if you look through this region, the flux of background sources is magnified. So they're lenses. So you see them magnified. So you can actually, these are of course small volumes, unfortunately, but are highly magnified. But if you look through that and you chance to find a source, high redshift source will likely get magnified and will come into view. Something that you could never see otherwise. Right? So in our 2017 paper, in a throw-off, we said, well, if nature was going to be kind to us, we'd find one of these OVGs. The way to detect that at redshift 9 or 10 would be if it was behind a lensing cluster. It turns out, of course, JWST is doing a systematic sort of survey of the lensing clusters, and all the highest redshift objects to date have been found behind these lensing clusters. Guess what? They found one. Well, they found several lensed sources, and they have found 3 sources at redshift greater than 10. So one is GHZ9, and one is UHZ1, and the other is GNZ11. So these are 3 accreting black holes that we have discovered at redshift 10. They're very different properties. So one key thing that I forgot to mention about our direct collapse black holes and these overmassive galaxies is that they have to be X-ray bright, because remember, we are dominated by the emission, by the accretion onto the black hole and that emission. So they not only would they be have to be detected in JWST, they have to be detected in the X-ray. So that was a key prediction. We were super nervous, right? Because what if Chandra died before JW, whatever, right? And Chandra luckily has not died, and it has provided us the bounty that we were looking for. So anyway, so GNZ11 was found. So this was at a redshift of 10.6, and the black hole mass there is about 10 to the 6 solar masses. So this black hole of 10 to the 6 solar masses, one can look and try to see what kind of paths, how could it have grown from a heavy seed or from a light seed, right? So these are models where people have looked at heavy seeds, light seeds, and see how you could have built up the mass of GNZ11. These are all the redshift 6 quasars detected by the Sloan Digital Sky Survey. This is that object GNZ11. And so what they show is that you could start with a heavy seed, that is this man, this is seed mass. Start with a heavy seed, you could grow in a completely garden variety way, and you could get there, okay? Eddington rate, nothing special needed in your conditions right around you, just, average amount of gas that is expected at these redshifts, and you could grow and get there. Or you could start with a very light seed, and then you would have to fine tune and have these super Eddington extra growth spurts to reach here. So you cannot really discriminate for this source. For this black hole, we do not know, we can't tell whether it came from a heavy seed or it came from a light seed. Why? It's not detected in the X-ray. So this is not going to be the kind of direct collapse black hole seed that we talked about. So that has to be detectable in the X-ray. This is not detected in the X-ray. Then there were these two other sources. This is the star of the show, UHZ1. This was detected at redshift 10.1. It has a black hole mass at about 10 to the 7 solar masses, and it has an X-ray detection at 5 sigma. It's detected in JWST and in X-rays in Chandra. It's lensed, and of course, the reason we detected it in the X-ray, because remember, lensing is achromatic, so you're magnified in X-rays as well. So you're magnified, this is what helped us, magnified by a factor of 3.8. So that brings it into view. So this object was discovered by Akush Bogdan, who's an X-ray astronomer at the CFA. And we had put in a proposal to look behind one of these lensing clusters, Abel 2744. This is a cluster that I have modeled and knew very well. And it was a very massive cluster. And we picked that one as a candidate. We applied for Chandra data as James Webb data was coming along. And this source was detected in that. So we were ecstatic. In fact, when he called and he told me, I actually did not believe that he had, so, you know, he actually teased me and he played with me and he actually showed our model and said, well, you know, I'm trying to read that model off your paper and I can't read it, you know. And I said, oh, I can send you the data. Why are you using WebPlot digitizer or whatever it is? And I said, yeah, I can send it. I started fishing around for the data while I was talking to him on Zoom. And he said, Priya, this is the data from JWST. And I literally fell off my chair. I'll show it to you in a minute. So for this particular source, for these two sources, so this is marginally detected also in the X-ray, GHZ9, and that has a black hole mass, we think, greater than 10 to the 7 solar masses in place at redshift 10.8. And this one is magnified by a smaller factor, 1.26 or so. So these are the growth curves for these, you know, once again, you start from a low seed mass, a heavy seed mass, and this is where UHZ1 and GHZ9 are. And what you find is that you would need to really grow at twice the Eddington rate throughout its lifetime to get there. Okay. Anyway, this is the data. I'll go through it quickly because I know I'm going over time now. So UHZ1, we were able to, because there was an X-ray detection, we argued in a paper that this is evidence, compelling evidence for a heavy seed. And then we were able to work out all the numbers and show how you could account for all the observed fluxes in the X-ray, the JWST bands, and so on. So this is that picture. So this was, it's a classic, it was our classic case. And let me show you the data. So this is one of Fabio's models for a UHZ1 in red. It's an overmassive galaxy that is garden variety fed at the Eddington rate. And this is the data of UHZ1 from JWST. It's really quite remarkable. And so, but it's not just this piece of data. As I said, these are the various pieces, predictions that it had to satisfy this source. So it had to have an X-ray flux that was detectable. So this is the prediction. This is the prediction if the model is in black and the detection X-ray Chandra limit is in blue. This is the JWST flux. And then it also had to have, as I said, because of the relationship between the stars and the host galaxy, it had to have a very particular, sit in a particular space where it had to be dominated by X-ray. This is the flux in a particular band and a color, and it had to be above this. It had to be an X-ray dominated source. So it satisfies all these properties. Anyway, so let me just come to the end and say, so at the moment, we think there's very interesting evidence for at least one or maybe two sources, GHZ9 as well, that likely originated from direct collapse heavy seeds in the very early universe. I am by no means claiming that that's the only way to make black holes, and I've repeatedly told you that there are multiple ways, but it appears that those two cases look to be compelling. So the other kind of issue, right? So as you can imagine, they have had a lot of pushback about, you know, light seeds, why not? So it turns out once again, in simulations where people have looked at light seeds, they just do not grow and they're never bright enough to be seen by JWST. So then people started looking at sort of fine-tuned models. What if you start with a light seed for UHZ1 and start building it up with many kind of fine-tuned super Eddington growth phases? it turns out that you can account for the mass, but you cannot account for the relationship between the host galaxy stellar mass and the black hole mass. But you do that simultaneously, right? Because that's what we're measuring. So right now, there are these two interesting cases where it has been claimed that super Eddington accretion might be in operation. So, but these phases are expected to last for a very brief period of time, just because the amount of gas that you need. Anyway, I'll just wrap up here because the challenges, so I've mentioned that as we've gone along, which is, simulations do not get black hole growth right at the moment, which is why Hayden's work is so important in trying to implement. So simulations cannot even reproduce the population of black holes that we are seeing. Their masses, the settings, the environments, their host properties in the Sloan Digital Sky Survey black holes at redshift 6, even at 3. So we showed that even at 3, these simulations are not really working well. So I'll just close with this. It's very, very interesting that this is the relationship between the mass of the black hole and mass of the stars. And so this is the local relation, and this is 1%, 10%, 1%. And you see that a lot of the JWST sources at lower redshift than 10. So these are not the 10, so redshift 10 sources. At redshift 7, they are all looking to be overmassive. So this is not necessarily a sign of heavy seeding, because by the time you get to redshift 6, redshift 7, a lot of time has passed in the universe, and many, many dynamical processes have operated, accretion has happened. So it's not necessarily a signature of seeding. I think the signature of seeding is and this is from work by my students and research group at Yale. And we've been looking at various simulations. As I told you, I have a soft spot for Astrid because they do multiple ways of seeding. They've implemented the heavy seeds. And what you find, this is simulation results. This is the properties of the galaxies, the stellar mass in galaxies and the black hole mass. And notice that depending on your seeding, this model has very different seeding prescription. These relationships look very, very different. I just don't have time. I will just stop here and just say that, the future prospects are really, really exciting. And we're waiting for more JWST data. And of course, trying to get as many deep Chandra images so that we can start, cross-correlating to see if we can find evidence for heavy seeds. And I'm very sorry I went over time.
Maybe a couple questions. I mean, you mentioned aspects and philosophies and the whole slew of other simulations. And so my question would be, what do you think is needed? Because one needs to work, as I understand, on two aspects. One is the seed.
Yeah.
4, 5, 6, whatever you put, but the more crucial point is the resolution.
Yeah.
You will never, ever, I mean, it is immediately obvious into 300, it's wrong, because the world is so important. But I don't know about aspect. Same is.
Little bit better, but.
All these things that but it's only what is the aspect to get the resolution.
So no, that's a great question. So the way in which black hole growth is implemented in these simulations is done to solve another problem. Okay, so the feedback. So which is the impact of the radiation from the black hole on the stellar population and the gas that is around in the galaxy. Basically, massive galaxies in the universe stop forming stars, and they are just passively aging over time. So they are basically red and dead. They are not actively forming stars. In order to explain that, the more massive a galaxy, the more massive the black hole in it. So people are like, oh, there has to be some feedback mechanism between the energetic coupling between the black hole and the gas in the galaxy that prevents star formation. So black hole growth models are tuned in order to prevent massive galaxies So it's over efficient feedback. And what that's doing in some of these simulations is it's prematurely stunting the growth of the black hole. Because what happens with this feedback is that you heat the gas, you prevent stars from forming, and then you also shut off the black hole in the process, accretion onto the black hole. So you're prematurely stopping a black hole from growing. At least that's our diagnosis has revealed that this feedback is over efficient. And it's not correct anyway, because we also showed that the flows that are, I think Ralph, it's before you came, where I talked about the way simulations implement growth by accretion is any gas particle that crosses the Bondi radius is assumed to have been accreted to, and we are showing that only a small fraction of it actually makes it to the horizon. So I think they need a better subgrid model. So subgrid models are the ways in which these complex dynamical processes are implemented in simulations. So I think there's a real dire need for gain in resolution and better subgrid models. I think that combination is really needed. And we need to bridge scales. We really need to bridge the scales for gas flows. We really need to understand how gas from 1 megaparsec actually makes it to the horizon. And what fraction makes it, and what is the efficiency of feedback from that accretion that you actually get. Yeah, you need very different, you need to implement the physics better. And yeah, absolutely.
Yeah, so in black holes that go by accretion, I guess there should be some correlation between the mass and the spin. And I guess they can measure something about that from iron lines, and that would seem like it would be a very tight constraint. But maybe is that something that could be put together?
Processing, right? So you get a snapshot at some redshift. So present day nearby universe, you're getting these iron alpha, K alpha line measurements for the spin. But remember, the growth is cumulative growth, and the spin, you start with some natal spins, and then you evolve them. And that's the new paper by Angelo that I'll share with you.
I see.
We model that. So the problem is the cumulative nature of the spin that you actually measure, how that spin.
But it goes along with the mass, doesn't it?
It does go along with the mass, yes. It does go along with the mass, but it also goes along with the geometry that you assume for the accretion. So if you have like a torus type heating disk versus a thin disk, etc. So it's pretty complicated.
Astronomy is so hard.
It's messy.
You don't have symmetries.
Yeah, no.
No, but there is a symmetry. That's what I'm always looking for. I'm looking for the.
No, no.
Oh, if we're out of time, don't worry, totally don't let me know.
We just do it over lunch.
Yeah, we can ask it, I'll ask it.
You can ask the question, but I can.
Yeah, I was wondering how they measured the masses in the early universe.
Okay, maybe
It
let's-
was too-
Oh,
so
okay.
let's go for lunch.
Okay.
You can answer and then.
Oh, okay. So how are they measuring the masses? of
Like
the
when you
black
say
hole?
you have a 10 to the 6 solar mass black hole is D of
It's
10.
from the X-ray emission, and from the modeling of the spectral energy distribution. So if you assume that it's a black hole that is contributing primarily to the energy output, then the continuum level gives you.
Even without any sort of spectral features.
I mean, the spectral features help. The
Yeah.
spectral features obviously help. So, but the spectral features help, but a lot of the relationships between the full width, half maximum of some lines, etc., it's all nearby universe calibrated,
Yeah, it's
right?
great.
So it's a bit worrying. So I think that the X-ray estimates are really quite robust. And then from the SED modeling, people have estimates. And in the case of UHG1, they coincided.
Yeah, it's time for you.